Hidden beneath this thin glass are clocks and physics that depend on Einstein. GPS is not just satellites and maps. It is a global choreography of atomic clocks, radio waves, and relativistic corrections accurate to a few nanoseconds. Over 24 satellites, each moving at nearly 4,000 meters per second, broadcast timestamps that let your phone locate you to within meters. This chapter lays out the anatomy. We will meet atomic clocks that keep time precise enough that light travels only a few meters during their error window. We will see radio antennas smaller than a quarter routing signals, wafer-scale chips etched at nanometer precision, and orbital platforms engineered to survive vacuum, radiation, and thermal swings of hundreds of degrees Fahrenheit. From the outside, GPS looks like a map. From the inside, it is applied relativity and material science. You will hear why engineers preset satellite clocks on the ground, why your phone corrects for ionospheric delay, and how 4 time-stamped signals become a single geographic coordinate. The goal is simple: turn time into distance. The challenge is brutal, and it relies on the deepest equations of physics. Everything starts with raw materials. Silicon begins as quartz sand, melted into an ingot by the Czochralski process, rotating and pulling at thousands of degrees Celsius until a single crystal forms. Engineers slice that ingot into wafers, thin discs measured in millimeters of thickness, then polish them to optical flatness. Copper and gold are refined from ore, drawn into wires, plated into RF connectors and antenna traces. Rare earth elements, like neodymium, become magnets for tiny motors and vibration stages. Lithium and cobalt power battery cells that keep receivers alive on the ground and in space. For the satellite body, aluminum and titanium alloys provide stiffness at low mass, resisting launch accelerations that exceed several g. Quartz crystals, the heart of every oscillator, are cut to micron precision and temperature compensated to maintain frequency. Even the glass over your phone is chemically strengthened, ion exchanged, to resist impact. Each material is selected for predictable behavior: thermal expansion coefficients, conductivity, and corrosion resistance. This chapter follows the transformation: crude sand to polished silicon wafer, raw ore to plated antenna, and brittle quartz to a tuned oscillator cell. Every choice influences timing, signal-to-noise, and ultimately, the accuracy of position. This is where function is written in light. Photolithography sculpts billions of transistors across a wafer. Engineers coat silicon with photoresist, align masks with sub-micron precision, and flash ultraviolet light to transfer circuit patterns. Chemical developers reveal the pattern, and ion implantation changes local semiconductor doping to form p-type and n-type regions. Layers of metal are deposited and planarized using chemical-mechanical polishing, creating interconnects only a few nanometers thick. For GPS, radio frequency integrated circuits, RF ASICs, include low-noise amplifiers, mixers, phase-locked loops, and correlators optimized for L1 and L5 GNSS bands. These chips must detect signals with carrier-to-noise ratios often below 0 decibels, then digitize and process them in real time. Packaging follows: wafer dicing, flip chip bonding, and electromagnetic shielding to prevent crosstalk. Heat dissipation is designed into metal planes and thermal vias. The precision here is staggering: alignment tolerances measured in microns, gate oxide thickness measured in angstroms, phase noise budgets calculated in fractions of a hertz. Every fabrication choice manipulates signal fidelity and timing jitter, the tiny errors that would grow into meters on the ground. Time is the product. Atomic clocks are the beating heart of GPS. Rubidium frequency standards and cesium beam clocks rely on quantum transitions measured in microwave cavities. Manufacturing an atomic clock begins with a vacuum cell, evacuated to near-zero pressure, housing vaporized alkali atoms. Magnetic shields isolate the cell from Earth's field. Microwave cavities spatially shape electromagnetic fields so atoms absorb and emit at a specific hyperfine transition frequency. Electronics lock an oscillator to that atomic resonance using a feedback loop called a servo. The result? A clock that may drift by only a few parts in 10 to the 13th or better. In space, redundancy dominates. Satellites typically carry multiple atomic clocks, 2 rubidium clocks and 1 cesium clock, to survive single-point failures. Building these devices requires cleanroom assembly, precision glasswork for the vacuum cell, and temperature stabilization to within a fraction of a degree Celsius. Each clock is characterized with Allen variances plots, phase noise curves, and lifetime radiation testing. In the phone, we replace these with temperature-compensated crystal oscillators, engineered to provide a stable reference that, when disciplined by GNSS signals, yields precise timing for navigation and synchronization. A GPS signal is weak by the time it reaches Earth, often less than a picowatt. Antennas and filters decide whether that whisper becomes usable data. Satellites broadcast on precise carriers, L1 at 1575.42 MHz, and newer signals on L5 near 1176.45 MHz. On the phone, ceramic patch antennas, printed loop traces, and active tuners capture these bands while rejecting local interference. SAW and BAW filters shape the frequency response, while low-noise amplifiers raise the signal above thermal noise with minimal added phase noise. After amplification, mixers down-convert RF to intermediate frequency, then analog-to-digital converters sample the waveform for correlation. Engineers tune antenna impedance to fractions of an ohm, control VSWR, and manage ground plane interactions within millimeters to avoid pattern nulls. At the system level, multipath, reflections from buildings, creates delayed copies of the signal. Signal processing uses correlators and matched filters to detect code faces within a few nanoseconds. Every filter pole, matching network, and antenna trace is an engineered compromise between size, sensitivity, and selectivity. This step is where physics meets layout and where small mechanical changes produce large positioning errors if neglected.
Assembly transforms parts into a functioning system. For satellites, integration begins with the payload deck. Mount atomic clocks, affix high-gain antennas, install RF distribution networks, and connect power from deployable solar arrays. Structural panels are torqued to precise specifications. Thermal straps are routed to manage temperature swings of hundreds of degrees Fahrenheit between sun and shadow. Ground testing uses harnesses and electronic interfaces that emulate space signals. In contrast, phone assembly is high-speed and minute. Pick-and-place machines position chips within tens of microns. Solder paste is deposited with stencils, and reflow ovens heat PCBs through precise profiles to form reliable metallurgical bonds. Antenna modules are calibrated and tuned using network analyzers to achieve the intended return loss and radiation pattern. Firmware is flashed to control GNSS correlators and timing stocks. At both scales, connectors are crimped, bolts are torque-checked, and alignment is verified with optical metrology. The logic of making is visible here. Tighten, align, secure, and verify. Each connection is a potential timing error. Each thermal interface influences the stability of the clock and the fidelity of the radio chain. Here is the math that makes coordinates possible. GPS timing is so precise that relativistic effects are dominant, not negligible. Satellites orbit Earth at about 3,900 meters per second. Special relativity says moving clocks run slow by roughly 7 microseconds per day at that speed. General relativity says a clock higher in Earth's gravitational field runs faster by roughly 46 microseconds per day for GPS orbit altitude. The net effect is about 39 microseconds gained per day. If uncorrected, that would translate to position errors of kilometers. Engineers compensate in multiple ways. Satellite clocks are preset on the ground to run slow so that in orbit they match GPS system time. Receivers apply relativistic clock corrections from ephemeris data. There is also the Sagnac effect. Because Earth rotates, signal propagation times depend on receiver longitude and must be corrected to an Earth-centered inertial frame. Finally, ionospheric and tropospheric delays, caused by charged particles and water vapor, slow the signal by tens to hundreds of nanoseconds and are modeled or measured using dual-frequency techniques. The result is a system that literally computes light travel time with Einstein's equations folded into the firmware and broadcast ephemeris. Before signals guide a plane or your phone, systems face brutal validation. Satellites undergo vibration tests that simulate launch, exposing components to hundreds of G in shock and sinusoidal vibration across wide spectra. Thermal vacuum chambers cycle hardware between extremes, sometimes over 100 degrees Celsius, while radiation tests expose electronics to proton and electron fluxes. Atomic clocks are run for months in environmental chambers to map frequency drift and aging. On the ground, GNSS receiver chips are validated in RF anechoic chambers and with signal simulators that replay complex scenarios, urban multipath, ionospheric scintillation, and spoofing attempts. Time transfer labs compare satellite clocks to ground standards using two-way satellite time and frequency transfer and precise carrier phase timing. Position accuracy is checked using geodetic-grade receivers referenced to survey monuments with centimeter-level truth. Software-in-the-loop testing injects ephemeris errors, leap seconds, and satellite outages to verify receiver robustness. This chapter shows the brutal reality. Validation is not optional. It is how you trade a box of parts for a trusted source of global position and time. Turning time into coordinates happens inside your phone in a few steps. A satellite broadcasts a pseudo-random code and precise timestamp. Your receiver locks onto that code, measures the time delay, called the pseudo-range, by correlating the incoming signal with a locally generated replica. Because radio travels at the speed of light, 299,792,458 meters per second, every nanosecond of timing error is about 30 centimeters of position error. To solve for 3 spatial coordinates and receiver clock bias, the receiver needs 4 or more satellites. The phone downloads broadcast ephemeris, satellite orbit, and clock parameters, and applies relativistic and atmospheric corrections. Carrier phase tracking refines the solution using the carrier wavelength for centimeter-level precision in survey-grade receivers. Modern phones fuse GNSS with inertial sensors and map matching to reduce multipath and urban canyon errors. Augmentation systems like SBAS or RTK services send correction data to tighten accuracy to decimeters or better. The software stack prioritizes robustness, detection, acquisition, tracking, and a navigation filter that estimates position, velocity, and time. The engineering payoff is elegant. A handful of faint radio bursts converts to an accurate, real-time location on a dynamic, rotating planet.
This final chapter pulls the threads together. GPS is an engineering triumph, a system that converts time into position using hardware built from sand, ore, and specialty glass, fashioned into atomic clocks, RF front ends, and silicon chips. It requires precision manufacturing, photolithography at nanometer scales, vacuum-sealed clock cells, and microwave cavities machined to sub-millimeter tolerances. It demands systems engineering, orbital mechanics, thermal control, and redundancy to survive launch and years in space. Most striking is the role of fundamental physics. Without special and general relativity, your map would quickly drift. Without corrections, errors of kilometers per day would accumulate. Engineers bake Einstein's corrections into satellite clocks and receiver firmware so that your phone need not solve tensor equations, just apply published ephemeris and correction terms. Finally, validation proves trust. Vibration, thermal, radiation, and time transfer campaigns certify that these components yield reliable timing and positioning. The outcome is practical magic, the high theory of Einstein made every day, guiding taxis, farmers, and emergency services. From sand to silicon, from equations to apps, GPS turns abstract physics into a coordinate in your pocket.
I hope this deep dive gave you a new perspective on the strategies and the relentless mindset behind these global icons. If you enjoy deconstructing business empires and tech legends in this Tech Archive style, make sure to hit that subscribe button and turn on all notifications. That way, you will never miss a new blueprint of history. For those of you ready to explore more boardroom coups and technological breakthroughs, I have handpicked 2 videos for you right here on the screen. Click one to keep watching. I will see you in the next one. Thanks for watching.